Hello everyone, it is still August 1st, 2022 as I record this, but I don't know when it'll be coming out. It is Geo-Rant time, but it is not Geo-Rant number 178. It is Geo-Rant number 179. And I'm going to talk a little bit today about supercontinents, but I need to get some things here out of the way real quick. Those of you know that we spent about a year trying to define what a continent was and a supercontinent. For all intents and purposes, a supercontinent is when 80% of all cratons exist in one continental landmass. Something like that. Close enough for what I'm going to be talking about here. Okay, you'll never get 100% of all land masses connected together. You always have volcanic arcs. You'll always have hot spots out in the middle of the ocean, Hawaii, stuff like that. So you're never going to have 100% of everything in one area. That doesn't happen and never has happened. But you might have heard of what's called a supercontinent cycle. Basically, continents break up, they reassemble, they break up, they reassemble to these supercontinents. Well, it's not as simple as that, and I don't really like that term because even though I agree that a cycle is a legitimate term for that, when you hear cycle, people think of rhythmic patterns. 1 RPM of a wheel per second, or 20 or 30, something rhythmic, repeatable, nice and predictable like that. 1 revolution of the earth around the sun in 365.25 days. But it's not a cycle like that. You can't sit there, people sit there and toss out, about every half billion years, but that's BS, because the margin of error on that's about plus or minus, 150 million years. So it's not a rhythmic cycle, and a lot of times the supercontinents don't last that long. Like it's a time frame of a supercontinent. Like continents will come together and they'll brush along, break back up, and then they'll come back together. So we could be talking about a supercontinent, give it a name, and give it a 100 million year span, but in reality, it's broken up and moved around in that 100 million years. Now, when I say supercontinent, the vast majority of your mind is going to pop to Pangea. And that is the most recent supercontinent. In our definition of what a continent is, we did propose megacontinent for stuff that's about, I don't remember. We'll put it this way. Once Africa hits Asia, we'll have a megacontinent again, but not quite a supercontinent. So we have Pangea, okay? And that's one everybody's familiar with. It's the one that eventually broke up as the dinosaurs during the Mesozoic, but it formed, circa about 300 million years ago, somewhere in that area. So, Carboniferous, Permian. And I don't study this one. I don't care. And you heard me talk about a supercontinent cycle, and you may have heard that term, but you may not be aware that we have named several other supercontinents in the past. And we, other than Pangea, which we've got the configuration of this thing pretty good. 300 million years sounds like a long time to people who study, vertebrate paleontology, but to us Precambrian guys, that's recent. All right. Before that, we have one called Rodinia, and we argue about when this one was or so, but estimates range from about 1,000 million or billion years to go to about, 750, I think it is, somewhere in that area. This is the one that helped, that was around post-mid-continent rift or whatever. And we are finally getting a lockdown on the configuration of this thing. And the fact that we can do that tells us we have plate tectonics in operation then. Now, those of you who heard me talk about before, anything greater than 3.2, or we'll just do 3,200, we'll stick with the million years, or 3.2 billion years, is pretty questionable. And probably anything up to 2,500 million years ago is iffy at best. Now, I'm in this school of thought that we had essentially modern plate tectonics at this time. There are others that even put it here. All right, but I'm with here. But this time, greater than that, probably not. Okay, so you guys may have heard of a supercontinent in there at about 300 million years ago, or 3,000 million years ago, 3 billion years ago, called Ur, which basically, it's BS, okay? There's really no way to know that deep. We don't have that in there, and the whole configuration of the thing, which sometime I might do a more in-depth video on. It's based on one paper, and everybody just keeps repeating it, and I hear scientists repeating it as if this was a confirmed physical thing. It's not. And the configuration is conspicuously exactly like a part of Golgonda during Pangea. Now, that's a lot of time, but that's not really enough time to reconstruct something that existed 10 times earlier. You know, it's really weird that Ur happens to look a lot like a certain part of Pangea and Golgonda. That's a really bizarre coincidence, all right? So I don't think it's there. Now, Rodinia, we are starting to get locked down due to paleomagnetic data. I have worked with people on this. I have helped them in the field collect paleomag cores. Basically, you take a small coring machine, which you can use as adapted chainsaw. You go into the rock, you record in the field its present orientation, okay? Then you take that core back and you date it. You can date it if you can, and you can get its reliable location. Now, people sit there and like to say, well, paleomagnetic data, how do you know we had a bipole, magnetic system like we do today? You're talking a billion years in the past. Yeah, but the fact when we do these and we plot these, like say this is the Earth here, here's our equator, some longitude lines for you, some latitude lines, you get it, right? When we plot these things, and we know plate tectonics was in operation then, we can follow a certain region. Like you might sit there and be like, well, the ocean crust gets consumed. How can we get paleomag data this far back when our oldest ocean crust is about this much, and it's in a little tiny area of the Mediterranean? We use mafic dikes from dike swarms, lips, large igneous provinces, things like that. We sample those on the continents because they can lock in that position too. Sorry, excuse me. And then we'll plot those, and we might get like 1300 here for a certain location, and we might get here at 1200 a certain location, and maybe 950 here for a certain location. And you see it follows a pattern. And we might get another nearby location that might give us a line like this, which is something we would expect if we were getting continents coming together. And since we get nice paths and don't get a bunch of random points anywhere and everywhere, that tells us that not only did we have a bipolar magnetic field, but we had continents moving about in similar manners that they do today. So we know that for Rodinia, this was the case. Rodinia is one of those ones that may have been a bunch of ones that kind of glided and moved past and then came back and did weird things like that. So that's why this huge time frame. We're getting it locked down, but we don't have it there yet. Now, contrary to popular opinion, even though if you Google supercontinents, you're going to get a whole list on things like Wikipedia. There's only one other that we know of for sure. And that has a duo name for some weird reason. Noona, aka Columbia. These are the same things. I think I knew the reason at one point, but I don't remember it anymore. I prefer Noona because I think it's a cooler sounding word, Noona. And we have so many things named Columbia that I just don't care. All right, so I refer to it as Noona. Noona was circa, I want to say maybe, oh man, I've completely forgotten. I want to say probably about 1500 MA to maybe 1400 MA, somewhere around there. This one we don't have a firm continental arrangement for at all. We just don't know it was there. People are starting to work on this, but the further you go in the past, the less things are preserved in their original state. Especially, we know we could have a ton of dike swarms during Noona, but they've been highly metamorphosed, so you get a bunch of wacky data, as opposed to here where they're less metamorphosed, and here even less metamorphosed. All right, but this is doable. I think probably in 10 to 15 years we'll have a good reconstruction for this. I think in about 5 to 10 years we'll have a good one for this. This is a time frame that you guys have heard me talk about. Oh, let me get a more appropriate color marker. Baraboo. Those Baraboo quartzites, that new paper that just came out that I'm a co-author on. Let's not use pink. Baraboo quartzite is purple. This is going to be pretty dark. It might even look black to you. But let's use Baraboo. The Baraboo interval quartzites, which also include the Sioux. How do you spell that? I don't even know anymore. Am I coming or going? The Waterford is one. We have the Barren, which I believe is spelled like this for some reason. We have the Barren one. We have the Thunder Mountain. I like that place. That's a cool place. Thunder Mountain, quartzite. You get the idea, etc., etc. There's a bunch of these throughout Wisconsin, Minnesota, and partially in South Dakota. Okay, and south of a certain latitude, like the Baraboo, they're highly deformed. They were deformed in some sort of mountain building orogenic event. But north of that, they're more or less level. I mean, there's a little deformation, but not too much. So that paper has to do with this supercontinent. And now we think an important part of at least megacontinents, maybe not necessarily supercontinents, but megacontinents and their formation, are these vast eroded sand sheets. Like at the end of the Paleozoic, or at the beginning of the Paleozoic, my bad, you had this breakup. Oh, wait, am I wrong here? Oh, gosh, Steve, what am I? Okay, no, beginning of the Paleoproterozoic. So at post-Rodinia, you still had some megacontinents going around. That beginning of the Cambrian, you had all these seas transgressing. You got continental stability. You got a lot of sandstones, at least over Laurentia, aka North America, over huge scales. But you also got things like carbonates and things like that. It wasn't just a big sandstone sheet that pretty much covered North America and large other parts of the world after the Great Unconformity formed, which I've talked about how there's multiple Great Unconformities depending on where you are too. It's not always a consistent time span, okay? It's not rhythmic. The Great Unconformity in some places isn't really a Great Unconformity at all. It might be 50 million years. Some places it's completely absent. Some places it's 2 billion years, things like that. But anyway, that apparently has happened in the past before. If we're right about Baraboo and those detrital zircons, and we're getting detrital zircon ages of things like, of ages about 2,500, or I think this is another one, maybe 1950 might be one. I think there's some of these. I could be wrong. I don't remember the exact numbers. But we're getting older than Pinokian orogeny dates. This indicates that our source area wasn't from the south, because we had that orogeny, the Baraboo quartzite, metamorphose through a collision during probably the formation of this, around this time. They weren't really coming from there yet. At the end of the orogeny, they would. But in the beginning, they were coming from here, and throughout they were coming through. We get these older ones, which could only have been sourced from way to the northwest, like the Slave Craton area and Northwest Territories, stuff like that. So if that's the case, that quartzite layer, which is a quartz sandstone, a lot like the basal sands of the Cambrian are, existed over Laurentia then as well. It's just been mostly eroded. I think I'm explaining that coherently enough. So recognizing those in the past may be a key to understanding these. Past this, you guys have probably seen, other names tossed out there for supercontinents. Kennerland, which is circa supposedly 2,500 million years ago. Beginning of the Proterozoic, stuff like that. A couple others sprinkled throughout there. But honestly, yeah, And somebody did a paper, I think, not too long after Ketterland was proposed, suggesting that it might actually have been 2 or 3 megacontinents, you know. And the further we go back in time, the less cratons we have too. We have less land, and that's a talk for another time. So, you know, you see these other names thrown out there for supercontinents, and like I said, you know, this one, and you look at this, and coincidentally, 500 million, 500 million, close to 5, or you skip, but I think there's one at 2 billion, I forget. So what it's called though. So you get these 500 million, 500 million, it gives you that impression of a rhythmic cycle that doesn't really exist. Like this probably wasn't even there. And this is probably several continents that never really came together. But we haven't even really begun to dig into this yet. So I could be completely wrong. So supercontinents aren't just Pangea. All right, we do have firm reconstructions or works in progress of a couple of others of the geologic past. So we can say with confidence we've had 3 supercontinental configurations during Earth's geologic history. We really can't go back further than that. It's like I've told you all before, we aren't even sure there was plate tectonics, you know, definitely older than that, and maybe even older than that, okay? So we can't just sit there and say, oh yeah, Earth's a big rhythmic system, boom, boom, plates, open, spreading, you know, continents, splitting, coming together every time. Because if that was the case, we'd have figured all these configurations out a long time ago. Anyway, that's it. If you have any questions or comments, please leave them below. And as usual, I hope you guys learned something.